Thank you, Kedar. It's always a pleasure to visit here. Inadvertently, I seem to have timed it in such a way that almost everyone is traveling, but for those of you who are still here and showed up, thanks for coming. How many of the students here are condensed matter students? 4. And the others, do you do all string theory? Okay. So I just learned that this is a joint string condensed matter seminar. So hopefully there'll be parts of this that are unfamiliar to everyone in the room, but hopefully parts that is familiar to everyone in the room. So the work that I'm going to talk about was done with primarily with a postdoc at MIT, Gen B, and a graduate student, Ethan Lake. We've written one paper, and there's another that we are trying to write. Some point it will be written. And we had wonderful discussions with my colleague Max Metlitsky, who's a condensed matter theorist, and with Nati Seiberg, who's an honorary condensed matter theorist. And okay, this is not working from here. It did work. So since some of you are not condensed matter theorists, I thought I would start with a brief crash course on condensed matter physics, 10-minute introduction to set the stage. In condensed matter physics, we usually know the UV degrees of freedom in the system. Microscopically, we know what the system has, what the relevant degrees of freedom are. It could be electrons, it could be spins on a lattice, it could be bosons. They could be on a lattice, they could be in the continuum, all kinds of things. And we're interested in the low energy properties of the system, the phases and phase transitions of the system with a known set of UV degrees of freedom. So at low energy, we can ask about how to categorize the various phases of matter can form in such a system. And that's a useful categorization in terms of the concepts of broken symmetry and long range order, which are characterized by Landau order parameter. So the most familiar examples are ferromagnets or antiferromagnets, where there's a definite pattern of spin orientation, and this is the concept of Landau order. Okay, so Landau understood how to think about broken symmetry phase of matter long back, and introduced the notion of order parameter. And these kinds of broken symmetry phases, for instance, ferromagnet has been known for several millennia, because the solid is a good example for broken symmetry, crystalline solid, good example for broken symmetry phase, also known for several millennia. Now, in the last 30, 40 years, it's become clear that this Landau notion of broken symmetry in an ordered and Landau order is not sufficient to describe all possible phases of matter. And there's various kinds of non-Landau order that we talk about in condensed matter physics. The simplest example is what's known as topological quantum matter. And a reasonably good definition of what topological matter is, quantum matter is that the low energy effective theory of such a phase is the topological quantum field theory. And this has been known, such phases of matter have been known since the 1980s. This guy is doing something. Yeah. So the most famous example is the fractional quantum Hall effect, which occurs in a two-dimensional system of electrons in a strong magnetic field. And the phenomena associated with the fractional quantum Hall effect are the quantization of the Hall conductance. That's what gives it its name. Now, other interesting things happen. Even though the microscopic system, the UV degrees of freedom, are only electrons, in a fractional quantum Hall system, there are emergent quasi-particles which have anyonic statistics. They have fractional statistics, and they have fractional quantum numbers. At spatial boundaries, there are gapless modes that go one way. They're described by a chiral conformal field theory. The low energy effective theory of a fractional quantum Hall system is Chern-Simons theory, which is a well-known topological quantum field theory. This is reacting slowly. A simpler example of topological quantum matter, something that has been discussed extensively in the last decade and a half. It's what's known as symmetry protected topological phase of matter, SPT. And the phenomena here is slightly different from the phenomena in the fractional quantum Hall effect. There's a gap ground state, just like in the fractional quantum Hall effect, but with trivial excitations. There are no anyons at all in the system. All excitations only have trivial statistics. They basically have the same statistics as that of the underlying particles and composites of those particles. But nevertheless, there's interesting physics at spatial boundaries, and similar to the quantum Hall systems, but despite not having any anyons or any non-trivial excitations in the bulk. And for this class of phase of matter, the distinction with the completely trivial ground state is protected by a global symmetry in the system. Yeah?
So, the symmetry in the language of Chern-Simons theory, can I think of the SPT phase as the one with the determinant 1, the determinant of the level matrix being 1, so that there are no anionic excitations?
Right. So that's a slightly more general. That's slightly more general than an SPT phase. A good example is of something that you just said is U1 level 1 theory. Right? It's a trivial theory, no anyon excitation, and of course the determinant is 1. Now that state doesn't need any symmetry to protect its distinction from other states. Right? It's an integer quantum Hall state. Right? Then condensed matter, we call it integer quantum Hall state. You can break charge conservation, you can break all symmetries, but it's still sharply distinct from a trivial state of matter. Right? So that's SPT states are a subclass of a broader class of states of matter known as invertible phases. So determinant 1 just means it's part of invertible. It need not be symmetry protected. Right? So symmetry protected is a subclass of invertible states of matter. Right. So a good example is what we call a bosonic theory, that shows an integer quantum Hall effect. It would be, a theory with two U1 gauge fields which have a mutual Chern-Simons term. So, there's a K matrix in order K, which is 0, 1, 1, 0. So determinant is 1. But there's a global U1 symmetry that's realized in this theory in a certain way, in such a way that for a background gauge field, U1 gauge field that couples the global U1, there is a Chern-Simons term at level 2. Right? So that's an example of, it's perhaps the simplest example within Chern-Simons theory of a symmetry protected topological state.
Also, one more question, perhaps it's not relevant for that, but how much is known about the microscopic origin of this effective theory?
A lot. Certainly in the fractional quantum Hall effect, we understand it completely. Okay, not completely, but we understand it extremely satisfactorily.
Emergence of this particular effective theory from Coulombic dynamics?
Yeah, that's right. In the fractional quantum Hall effect, that's an old solved problem, right? So the topological structure of various experimentally seen ground states in the fractional quantum Hall effect, what TQFT describes it, there's a pretty good derivation that you can give starting from microscopics. Right? Of course, there's always room for improvement, but I think things are in good shape there. Now, for SPT phases, so you can write down wave functions, but there's various other things people have done over the years. You can do flux attachment, this and that, and derive effective field theories that, for all this large number of fractions that are seen in experiments, and most of them are described by abelian Chern-Simons theory with multiple gauge fields, and you can derive it all from microscopics in a reasonably satisfactory manner. I mean, it's an old mature field, right?
There are more than one microscopic theory for such
Sure. Yeah, yeah, yeah.
Which is what has given rise to this new developments in duality.
Yeah, so that's one way in which you can try to get to the duality. The dualities have to do with quantum critical points. Here I'm just talking about phases of matter. As far as these phases are concerned, there's many different descriptions, sure. But the new developments with dualities have to do with phase transitions, which are more delicate than just understanding the phase of matter themselves.
So, I mean, it's not like two distinct UV theories flowing to some higher frequency.
Oh, for phase of matter, that happens all the time, and we understand that in many cases quite well. Right? So the new things you're referring to is addressing more delicate questions about critical points, right? Different descriptions of the same critical point, which, yeah. Okay. This is not very efficient. Right. So you could think about it in, so think about the simplest such state, which is the px plus ipy superconductor, right, of spinless fermions that still has chiral edge states. Now take two copies of it, right, that has a complex chiral edge mode, which is just there. You can't get rid of it, right? And there's no global symmetry, nothing, right? That you can do disorder, you know, it's completely protected, right? Okay, now the second kind of non-Landau order is when you don't have a gap ground state. So there's a ground state and then there's gapless low energy excitations on top of it. Now the most familiar example of, so I like to call this non-Landau order 2. Oftentimes the order in such a phase cannot be captured by the Landau's order parameter concept. The gapless excitations may not be Goldstone modes of anything, right? There's no broken symmetry. And the best example is the Landau Fermi liquid. Now, there's still Landau's thing, but it's not the order parameter, right? As somebody once said, physics has to be consistent, physicists don't need to be. So, so Landau Fermi liquid is a great example of non-Landau order in the sense that it's a state of matter whose universal physics is not captured by thinking like a statmech person would do, saying everything is just order parameter. Is it ordered? Is it not ordered? Right? That's not enough to characterize Landau Fermi liquid. Okay? Now, recent years there's interesting variants of the Fermi liquid which are even simpler. It is, but the free Fermi gas is not trivial. That's the point. It's familiar, but not trivial. Right? So there are variants like Dirac materials, wild semi-metals, so on, which have emerged in Dirac or wild fermions in the system. But most striking are non-Fermi liquid metals, in which, unlike Landau Fermi liquid, there is no quasi-particle description of the excitation spectrum, and you can't use the language of elementary excitations and quasi-particles to characterize the low energy dynamics. So a good example of something that doesn't have a quasi-particle description is a strongly interacting conformal field theory in dimensions bigger than 1 plus 1. Right? There's no guarantee that you have any quasi-particle-like particle-like description of the spectrum. Right? But that's a very specific example that occurs when you have relativistic invariance, blah, blah, blah. More generally, you might have a Fermi surface, but no quasi-particle. There's all kinds of things possible. Right? And for these non-Fermi liquid metals, there's lots of experimental examples, but very little theoretical understanding. It's evolving slowly with time. We are learning more and more, but not anywhere as mature as topological quantum matter. Right? So I like to say this beyond topological order. Right? What should I do to get? Very good. Okay. So the focus of this talk is actually on critical quantum matter. Yeah.
How would one know whether there are quasi-particles in a applicable conformal theory?
How do we know that there aren't?
Yeah. How
Right. So
Because usually, from incoupled uniform field theories, we think in terms of radial quantization. So you put down a sphere and then look at the spectrum.
right.
But the question about quasi-particles is related to quantization of the theory on a
In flat space.
flat
Yeah.
space, right? So
There's one, if you had some control on this theory, so let's take a simple example where we do have some control. Let's take the ON Wilson-Fisher CFT in the large n limit. Not n equals infinity, but at large but finite n. You can do 1 over n calculations, you have control over the theory. So you can calculate something like the free energy as function of temperature, right? Now it's a free boson or free fermion, it'll have the same scaling, right? T to the power d, right? T to the power d, yeah. And but the coefficient is, there's a fixed number for the coefficient, right? For if you have n free bosons or n free fermions, right? Now if you calculate this coefficient in a 1 over n expansion for the ON model, you find a number that doesn't match any number of free fermions or free bosons, right? So that's a proof that there isn't an emergent free particle description of this CFT. Exactly, yeah. So this is a symptom of there not being quasi-particles.
but there could be some spectrum which is not quite that of the free particle, but when the states are far away, perhaps they behave. You can scatter. You can form some sort of asymptotic states which can scatter, which would make them in some particle states. Okay.
Yeah, I'm not sure exactly. I mean, there's no obvious free particle description of the spectrum. Not free particles. That's the point, right? So I'm going to talk about in this talk about critical quantum matter, which occurs at a continuous zero temperature phase transition between two phases, phase A and phase B. This phase transition occurs at zero temperature as you tune some parameter. So what happens is that there's a qualitative change in the many-body ground state as this parameter is tuned, and you go from one phase to the other phase. And in typical examples of such phase transitions, you lose the quasi-particle description right at this quantum critical point. A good example is just a theory where this phase transition is described by conformal field theory. Right? More generally, it won't be described by conformal field theory, current matter physics. It may not even be relativistically invariant. Right? Okay. Now, so this problem of quantum criticality has been studied for decades. So Kedar and I share a thesis advisor. He wrote the textbook on this topic, and despite that textbook existing, our intuition for what kinds of continuous quantum phase transitions can occur and how to describe them is extremely poor, right? So the textbook, what the textbook primarily deals with is a certain kind of phase transition. Okay? Yeah, Subir. The certain kind of phase transition where you go from a Landau ordered phase to a completely trivial phase. Right? For instance, in an Ising model, quantum Ising model, say Ising model in a transverse field, you go from the trivial phase to a Landau ordered state where you break the Ising symmetry. Right? And in this example, for such a phase transition, there's a well-developed framework to deal with it, which is essentially to write down a quantum Landau-Ginzburg-Wilson theory in terms of the fluctuating order parameter, and it's a long wavelength fluctuations of the order parameter that are blamed for all the interesting critical physics. Okay? What happened? Yeah, so something is going on. Yeah, okay, so this is good. So we've learned in the last several years that there's a lot of life in quantum criticality beyond this Landau paradigm. The simplest case where it's a no-brainer that this Landau order parameter fluctuation theory must fail is if one or both phases have non-Landau order. Right? For instance, if one phase is a fractional quantum Hall state, there's no order parameter description of the phase. So how are you going to describe the phase transition in terms of order parameter fluctuations? It simply cannot make sense. Now, a more surprising thing perhaps is that this it turns out that it's possible to have continuous phase transitions that are forbidden by Landau order parameter theory between two phases that are themselves Landau allowed. Right? So the first example that we encountered showed up in quantum magnetism, where there was a phase transition between nail ordered. So imagine you have spins living on a square lattice, spin half, moments living on a square lattice. Natural phase is a nail ordered state where the spins just do up down, feeds into that pattern. That breaks spin rotation symmetry. And then there's another phase which preserves spin rotation but breaks lattice symmetries, right? Breaks the symmetry of the square lattice, where each spin grabs a partner to form a spin singlet state, and these dimers line up in some pattern, and both phases, either phase is described by Landau order parameter, but within Landau theory, there's no reason to expect a direct continuous phase transition between these two phases. They break different symmetries, right? But nevertheless, it turns out that when you analyze this problem, it's possible to have a direct continuous phase transition. So it's an example where the Landau paradigm just fails, right? And Kedar's worked on this class of problems for many years, made a lot of important contributions. So the theory that describes this sort of critical point is what is known as deconfined quantum criticality. So what that means is that, so there is a field theory that describes this critical point, but this field theory is most simply expressed in terms of weird deconfined degrees of freedom that emerge just at the critical point between two phases, each one of which only has conventional excitations. So these deconfined degrees of freedom, in terms of which we write the field theory, may have fractional quantum numbers, even though neither phase has excitations with fractional quantum numbers. Okay? So there's many other proposed examples by now in 2 plus 1D. And it turns out that one thing, so we proposed this field theory long back, 15 years back. In recent years, it's become clear that very similar, and sometimes in fact exactly the same theories also emerge for phase transitions between trivial phases and this SPT phase of matter. Okay? Neither of which break the symmetry, but they differ by having, they differ in their global topological properties. Okay? Now, why the same sorts of theories emerge, we understand now. It turns out that these different theories related by these dualities of quantum field theories that we've learned about in the last few years. So that's the real reason why the same sorts of theories emerge in these different problems. Okay? I'm not going to talk about this very much. That's a separate long talk. But no. The field theories that describe, say, this nail to VBS transition, it turns out they have dual descriptions in terms of other Lagrangian descriptions. And in those dual descriptions, they arise as some version of a phase transition between trivial and SPT phases of the degrees of freedom in that dual description.
Would that also make a given side of the critical point dual to each other as a gap phase?
No, the gap phases in that particular example, the gap phases or symmetry broken phases. Sure, we have multiple different descriptions of that, of both phases, both symmetry broken phases. Now, what the duality tells us is that there's multiple descriptions of that critical point, and in some dual description, it gets related to a different phase transition, to a field theory for a different phase transition between trivial and SPT phases. Right? So there's an interesting story there, but I'm not going to, this is just for some context. Right? So what I'm going to talk about in this talk, so I have to say that this theory of deconfined quantum criticality, I wish I could declare victory and say that everything is understood. Right? But there's a lot of sticky points which have not been resolved despite 15 years of the best numerical work on the subject. In particular, for SU2 symmetric spin systems, it's not clear there is really a quantum critical point, a second order quantum phase transition that this field theory describes. Okay? So there's annoying problems with the numerics that no one really has understood. I think, so Kedar is the big expert on all this, but following the numerics for the last 15 years, it's been ups and downs. It looks, things look good, and then there's some other input, and then things don't look good. And the latest that we are learning is that it seems from the numerics that the theory may have some higher symmetry, an SO5 symmetry that one can understand again through these dualities and so on. And there's estimates for the numerical exponents from numerics, for the critical exponents from numerics. But then you follow the feet of the bootstrap people and say, look, is there an SO5 symmetric CFT with exponents in this range? That's right up their alley. And they say no. So there's a lot of confusion right now. But for SUN magnets, things look good, and there's a proof of principle that this kind of transition can exist. One just has to point to SUN for general n, and for n bigger than some number, everything is under control. Okay, so what I'm going to talk about are a number of surprising quantum critical phenomena that at least I had no previous examples of, and I'm not aware of examples in the literature, but if any of you knows of any example of these phenomena in the StatMech or condensed matter or field theory literature, I'd be very happy to hear about it. So the first thing I want to talk about is an example of deconfined quantum criticality, which is IR solvable. So we don't really need heavy numerics to decide what happens. So we know with complete confidence that this phenomenon happens. And furthermore, this is an example in 3+1 dimensions, for which previously we had no example at all. Right? All the proposed models, theories for this phenomenon were in 2+1 dimensions. The second phenomenon that I want to talk about is a situation where the phase diagram looks like this. There's a phase transition between two phases, phase A and phase B. Usually, for the same two phases, there's a unique universality class for a phase transition. Right? But once you specify the two phases, you know what the phase transition is like. Because it may be first order in some part of its phase boundary, and there can be a tricritical point and then it's second order. But many of us have wondered over the years whether it's possible to have multiple universality classes for the same phase transition, right? Where depending on which portion of the phase boundary you cross, the system is controlled by a different fixed point. Okay? Examples like this exist in disordered systems. You take a plus minus j spin glass, so this famous example. But in clean problems, none of us, at least no one I talked to, has ever come up with an example. But it didn't seem like it was forbidden by anything, right? Anyway, we'll find infinite number of examples of this phenomenon in this talk. Now, a third phenomenon that I want to talk about is what we call an unnecessary continuous phase transition. It's an interesting example where within the same phase, there is a phase boundary. Okay, what does it mean to have a phase boundary within the same phase? It's like the liquid-gas transition, which you can go around. Right? There's no fundamental distinction between a liquid and gas. You can go around it. But that's a first-order line that ends at a critical point, and you go around. Right? So here I'll show many examples where there's a second-order line that terminates, and you can go around it.
And the endpoint of the second-order line is then different?
It's a new universality class. So we haven't analyzed the endpoint yet, but that's such a so this is a quantum critical point that exists within a single phase of matter. Now, usually in quantum condensed matter physics, people who do experiments will often say, I do something, I see power laws, there must be a quantum critical point. So the obvious question then is, what is the distinction between the two phases on either side? So the existence of this example tells you that may be the wrong question.
So will a Lifshitz transition be of this kind, like Lifshitz point?
with Fermi surfaces?
Yes.
No, but then the two phases are different, right? You may have two Fermi surfaces that merge into a single Fermi surface.
No, I mean to say if some continuously developing wave vector appears
Or like a spiral that changes.
from zero,
Yeah, but then the nature of the phase has changed, right?
nature of the phase is changed.
Here the phases are exactly the same. There's no distinction between the two phases. But within a single phase of matter, you tune one parameter, suddenly you'll have diverging correlation length, there'll be power law correlations. It's amazing, right? But it turns out we find a lot of examples, an infinite number of examples of this phenomenon.
Does that mean in particular the conformity theory has exact marginal parameter?
No. So throughout this line, in all the examples we find, it's controlled by a single fixed point, right? With only one relevant operator and no marginal operators, because the end point is different, right?
It's got somehow to do with the topology of a region that is attracted by that fixed point. Right? That's the distinction. Not the fixed point is not, there's one fixed point.
There's one fixed point, exactly.
The region that's attracted by that fixed point separates two other regions that go to two other places.
Usually.
Here
But here it's the same thing.
those are some of the theory.
Yeah, exactly. Yeah, that's right.
It's the same fixed point.
Nothing
Nothing changes.
changes. It's in fact it'll all the first example we found was in a system of bosons where the phase itself is completely trivial. It's gapped generically. Everything is short range. There is no topological order. There's not even SPT order. It's as trivial as you can get. But then you tune one parameter within this phase. You hit this, hit this weird critical line. Right? We also have lots of examples in fermion systems, free fermions, blah, blah, blah. And not free fermions, but interacting fermions. Now, the fourth phenomenon that we encounter is like a fermionic analog of the Landau forbidden phase transition. If you think about phase of matter that can be described within band theory, meaning within a free fermion description, right? Now, there's various rules on what kind of phase transitions between band insulators are allowed to be continuous. Right? For instance, in the quantum Hall effect, integer quantum Hall, you can only shift the Hall conductance by one each time. There's a rule within band theory, within free fermion theory, that's the only kind of continuous phase transition. Generically, if your Hall conductance, the quantized Hall conductance jumps by 2, any generic perturbation will split it into two phase transitions. Okay? Now, it turns out that there's several examples of quantum critical points that are forbidden between band insulators that are forbidden within band theory, but once you allow interactions, you can have such a direct phase transition. Okay? And the final example, I probably not have time to talk about this, is a system which is undergoing a phase transition between a trivial phase and an Ising ordered phase, and which is otherwise trivial. So the transition could have been in the Ising universality class, but it turns out that if the system has another symmetry, let me call it G, and G acts trivially on the degrees of freedom in both phases, the presence of this extra symmetry G protects a new universality class, which is deconfined, and all kinds of weird things happen. Right? So even though the phase transition is Landau allowed, it can be second order within Landau theory, very just an Ising transition. It turns out that it can also occur in a different universality class. Okay?
So then that's related to this.
It's related to that, but it's a special example in a Landau allowed situation of this kind of thing. Okay? Now, I probably won't get time for this too, but so all of these are things that in stat-mech condensed matter we can, questions that, that within the field it's legitimate to think about. Right? It's legal if you're a stat-mech or condensed matter person to think about phase transitions. But there's a bonus that an outgrowth of this is that we are led to conjecture a striking possible duality of a strongly coupled field theory in 3+1 dimension to a very simple theory. Okay? So that's at a conjectural stage. We don't know if it's true, but we don't know, it's not obviously wrong, right? So, there's a lot of examples of supersymmetric dualities in 3 plus 1D, but not even a single example of a non-supersymmetric duality. So if this is right, then this would be interesting from that point of view as well. So I'm going to focus on theories in 3 plus 1 dimension. Some of the examples, we also have examples in 2 plus 1D, but it turns out it's easiest to find in 3 plus 1D, right? So I'll mainly talk about 3 plus 1 dimensions. I'm going to start with a very simple theory, the free Dirac fermion, and explain the methods that we use in this context, right? So hopefully everyone in the room understands, right? And then in talking about the real problems we deal with, I won't talk about the methods anymore, just talk about the results, right? But the strategy is always going to be the same as the strategy we use for the free Dirac fermion, okay? Okay, so the theory that we'll work with most of the time is a gauge theory, SU2 Yang-Mills theory coupled to matter fields, massless matter fields, and we'll develop an interpretation of this theory as a deconfined quantum critical point. Okay? So the strategy is sort of reverse from what we normally do in condensed matter. We start with the question and then we figure out the answer. Here we're going to start with the answer and then figure out the question. I don't know, is this what string theorists do? I don't know. Sometimes, yeah. But here it's a lot simpler. As you'll see, I'm going to work with the most trivial possible gauge theories, which are deemed so trivial that field theory textbooks don't ever talk about them. Okay?
This is not going to be Lang's
It will be even more, you'll see, it's even more trivial than that. And we'll generalize this to various other contexts, in particular change the gauge group and think about it. And the duality is going to be, the conjecture duality is going to be a duality between such an SU2 gauge theory coupled to some matter fields in 3 plus 1 dimensions when it's strongly coupled in the gauge theory description. And the conjecture is that it's dual to a free theory to augmented with a decoupled gap topological quantum field theory. Okay? Now there's a similar example that I knew about that helped formulate this in 2 plus 1D in a recent paper by Jaume Gomez, Komorgotsky, and Nati Seiberg. A very similar statement of an SU2 gauge theory in 2 plus 1 dimensions that's dual to a free Majorana fermion plus a gapped Chern-Simons theory. Okay? And that duality has a bit more evidence than the duality we are going to conjecture. Okay, so let's start with the free Dirac fermion in 3 plus 1 dimensions. So this is the Lagrangian, right? Single 4-component fermion. The kinetic term is just the usual one, minus I d slash. Now, so the free Dirac fermion has an obvious global symmetry, which is charge conservation, right? So as a probe of that global U1 symmetry, I'm going to allow myself to turn on a background U1 gauge field, just to probe that symmetry. Now I've learned in the last 3 years that whenever I give talks in front of string theorists, and when I have such a U1 gauge field that's coupled to a fermion, I should call it a spin C connection and not a U1 gauge field, right? I don't know, I know that it depends on which string theorist you talk to. I gave this talk at Stanford and Shamit Kachru tells me we should worry about that only at Princeton. But you are at Princeton, so. Anyway, it's yeah.
I guess perhaps makes, it would be more relevant if the space on which you are putting this is funny.
Yeah, I'm going to put it on funny spaces immediately. But for our purpose, what this really buys us, right? I'm not going to talk about this term spin C connection anymore. I'm not even going to define it. What it really does is it's a way, if you're not you know, in condensed matter physics, we know what degrees of freedom we have. We have electrons, and we know that everything with odd charge is a fermion, everything with even charge is a boson. And we don't think about it, it's sort of built into our blood. Now, if you don't know what your UV degrees of freedom are, but you want to keep track of precisely this fact, then knowing that it's a spin-C connection, it's a bookkeeping device to keep track of this fact. So that's all there is. It tells you something about how flux is quantized on manifolds with various, you know, arbitrary space-time manifolds. All right. So the dot dot dots primarily will allow for a mass term, because I'm only going to deal with the free fermion, right? So the mass term m psi bar psi, which will allow me to tune through a phase transition. Okay? And I'm going to allow myself, just as I allowed a coupling to a background U1 gauge field, I'm going to allow myself to place the theory on an arbitrary, smooth, oriented space-time manifold, right? Which is described by some metric, G. Okay? That's again just as a probe of the system. For condensed matter physics, it's a good way to keep track of things like thermal conductivity and so on, which are important in a full characterization of a gapped phase. Okay, so apart from the global U1 symmetry, the theory has various discrete symmetries in general. But in general, I mean in the presence of this mass term, right? And the discrete symmetry that I'm going to focus on is time reversal. And I'm going to focus on a choice of time reversal, which may be a bit strange, but it smoothly connects with other parts of the talk. And with this choice of time reversal, the electric charge is odd under time reversal, while usually we think of the electric charge as even under time reversal, right? So in field theorists often like to call this a CT symmetry, what I'm calling time reversal. But, you know, okay, it's an anti-unitary symmetry, so that's all I care about. Okay? So this is the theory we want to think about and understand how to interpret it as a quantum critical point. Okay? Very simple question. Okay. So in the presence of this charge U1 and time reversal symmetries, as the sign of the mass has changed, there is a phase transition. Okay? So for both signs of mass, you get a massive Dirac fermion, which it's clearly a gap phase. But when the mass is tuned to 0, there's gapless excitations, and so it looks like you're going through some phase transition. Now, what is the distinction between the phases you get for either sign of mass? Right? So it turns out there's a very sharp distinction in the presence of this symmetry U1 cross time reversal. If one side, you think of it as a trivial insulator, so we use the word insulator in condensed matter physics to just mean a system with a global U1 symmetry where the global U1 currents are dead. Right? There's no gapless fluctuations associated with the current of this global U1. So both sides are insulating phases because everything is gapped. But if one side is chosen to be trivial, then the other side is a topological insulator. Okay, it's an example of a symmetry protected topological phase, but in a free fermion system, it's one of the first topological insulators that was discussed 15 years back by Kane and Milley. Okay, so how should we understand this distinction between the two signs of mass? Right? So this is something that's there in textbooks. There's a very physical way to think about it, which is to think about a spatial domain wall between the two phases. Imagine you make the mass a function of space so that it's positive in one half space and it's negative in the other half space. Then where the mass goes to 0, you can think of it as a domain wall between the two phases with opposite signs of mass. And you can just solve the Dirac equation with this spatially varying mass, and you'll find that there are 0 modes that live at the domain wall, right? And what lives at the domain wall is the single two-component massless Dirac fermion, which is the thing that characterizes the boundary between a topological insulator and a trivial insulator. Okay? So that's the most physical way of understanding why there's a sharp distinction in the presence of time reversal between the two signs of mass. Okay? Now, in current matter physics, the same transition is usually described in terms of a band crossing transition. Right? So, two bands come and then there is a band inversion, and band inversion happens by the two bands touching each other. That is a Dirac point, and then the bands invert, and that changes the topological characterization of the band structure. Okay, so those are all physical ways of thinking about it. Now, for what we want to do, we want a more formal way of thinking about it, which we can generalize to more complicated problems. Okay? And the formal way is to derive the change between the two signs of M in the theta term that in response to these background gauge fields A and G. Now, a topological insulator differs from a trivial insulator in having a theta term for the background U1 gauge field at theta equals pi, and for the metric. But so we want to derive that change of the theta term when we change the sign of M by explicitly calculating the partition function. Okay? So this again is well known, and let me sketch how this formal derivation works. So there's some sort of review. There is a review of this in a recent paper by Witten. Though he's a string theorist, this paper is entirely about condensed matter physics. It's about field theory, the field theory description of topological insulators. But there's a review of things that were known a long time ago in the field theory community, but interpreted in the implications for modern topological insulator theory, that interpretation is more recent, right? But the methods are old methods. So what we want to do is to calculate the partition function of a free Dirac fermion of mass m, right? Now it's a free fermion, so the partition function is a determinant, right? It's a determinant of some determinant, and the determinant is d. It's a determinant of this operator d plus m, where d is d slash, right? And now minus I times d slash is a Hermitian operator, so it has real eigenvalues. So this determinant is simply a product over these eigenvalues. Okay? And remember that we are in some closed, smooth oriented manifold, right? So some bunch of eigenvalues lambda I. So G refers to the metric on this manifold, right? So it considers some arbitrary manifold, right? But for simplicity, I'm just using an oriented manifold. If you wish, putting it on a non-orientable manifold is a even better thing to do, but then it makes life more complicated, right? So let me not do that. Now, there's a gamma 5 matrix which anti-commutes with the master's Dirac operator, and because of this, all non-zero eigenvalues of D come in pairs. For each lambda I, there's a minus lambda I. Okay? Now, what we're interested in is the ratio of partition functions for positive mass and negative mass. This ratio of partition functions is the ratio of these determinants with positive and negative mass. And it's easy to see that all non-zero eigenvalues cancel out. Okay? So the only thing that's left are zero eigenvalues, right? So this ratio is then equal to minus 1. So if lambda I is 0, each 0 mode contributes minus 1 to the partition function. So it's minus 1 to the total number of 0 modes. Okay? Now zero energy modes, you can choose the helicity of zero energy solutions of the Dirac equation. You can either come with positive helicity or negative helicity, right? And the total number of 0 modes is sum of positive helicity and negative helicity 0 modes. Now mod 2, that is the same as the difference between positive and negative helicity 0 modes, right? So this means that the ratio of partition functions is minus 1 to the j, where j, which is defined to be the difference between the number of positive and negative helicity 0 modes, is a number known as the index of the Dirac operator. It's a topological invariant. Okay? So we see that this ratio of partition functions is a topological invariant. It's minus 1 to the j, and the relationship to the topological insulator story is that there is a theorem which tells you that this J has a nice local expression as an integral of some local thing, right? And that local thing is precisely f wedge f with the right coefficient, right? So and there's a similar term involving the metric. So you plug this into here, you get a theta term for the background U1 gauge field and a theta term for the gravitational for the metric. And these theta terms have exactly the right value. They correspond to theta equals pi. That tells you that if one phase is trivial, then the other phase is a topological insulator. Okay? So that's it, right? So the method we are going to use, that we've used throughout, is to calculate, even for more complicated theories, where we don't know how to calculate the partition function. It turns out that it's a lot easier to calculate the ratio of the partition functions with positive mass and negative mass. And that ratio will turn out to be a topological invariant that's independent of the detailed dynamics of the theory. Right? And that topological invariant is easy to calculate, even though both numerator and denominator themselves are basically impossible to calculate. Yeah, maybe not impossible, no one knows how to do that yet.
In this case, which is a matter of time?
Which one is, no, it's a matter of UV completion.
So you can complete it?
You can complete it in one way or the other. Right? So again, in the kinetic matter context, it depends on not just what happens near band touching, but what happens elsewhere in the Brillouin zone. Right? So same story here. So we'll always use the convention that the UV completion, which tells us that negative m is a trivial insulator. Okay? So we can generalize this in a simple way first, but before that, let me comment on the point of view that we are taking. Right? So this is a trivial theory, right? Free fermions. It can't get more trivial than that. But nevertheless, the point of view from which I'm going to view this and all the other theories is going to be different from what is common in the high energy community. So the massless Dirac theory has more symmetries than the massive case. Okay? So the massless Dirac fermion can be written as two Weil fermions, and then you can rotate between the two Weil fermions. It has all these extra symmetries. Right? Now I'm going to regard all those extra symmetries as emergent, and that the important microscopic symmetry is the symmetry at a generic point in the phase diagram. Okay? So this point of view is different from that in high energy physics, where everyone starts with the massless theory, and then everything else you regard as a weak perturbation of the massless theory. Right? So these extra symmetries of the massless theory survive in the IR when weak interactions are added. Okay? They are emergent symmetries of the IR theory that emerges at the critical point. They are not microscopic symmetries. Okay? And because these are emergent symmetries, they can be anomalous. Okay? So a good example for the free Dirac theory is the chiral anomaly that anyone who's worked on Weil semi-metals knows, and all field theorists know. More technically, they are what's known as the 't Hooft anomalies in the field theory literature. But in a kinetic matter system, no microscopic symmetry can ever be anomalous. Right? But emergent symmetries are allowed to be anomalous. There's no problem with that. Okay. So let's generalize this a little bit. So there's a very simple generalization first. If we have n free Dirac fermions, okay, we can think of that as 2n free Majorana fermions, and then the global symmetry is SO2n times time reversal. And once again, we can take the m less than 0 theory to be trivial, and then the m greater than 0 theory, if you calculate the ratio of partition functions, you'll find that there's a non-trivial theta term for the background SO2n gauge field. Right? Now the global symmetry is SO2, the continuous global symmetry is SO2n. So I can couple a background gauge field to this symmetry and ask about the theta term. And you can do the calculation. There's a non-trivial theta term, which tells you that the massless point of this theory is a quantum criticality associated with the trivial to topological phase transition of fermions with this symmetry. Okay? So that's an interpretation of the theory of n free massless Dirac fermions as a certain quantum critical point separating to a trivial and a topological insulator of these fermions. No, no. So the kind of mass term that I'm adding, just take, n free massive Dirac fermions. Right? When you write it in the Majorana basis, it has SO2n symmetry. Okay. So this is the exercise that we've done for the free fermions is the exercise we're going to do for all the other theories. Right? We're going to take known gap massless theories of matter or of known massless quantum field theories. The first question we are going to ask is the first question is what is this a theory of? It turns out that's the most basic question you can ask about any field theory. Okay, and we'll see examples of that, and then we're going to turn on mass terms, and then figure out what the two phases are, and then interpret this massless theory as a quantum critical point sitting between those two phases. Okay, that's what I meant by starting with the answer and then figuring out what question this answer answers. So we're going to study theories, SU2 gauge theories with NF flavors of fermionic matter fields, and two distinct cases. In one case, the matter fields will sit in the fundamental representation of SU2, and in the other case, the matter fields will be in the adjoint representation of SU2. Okay? And as we'll see, these are very different theories, and the interpretation is completely different, even though the Lagrangians look similar. Okay? I'm having difficulty with this. Yeah. So let's start with this theory. Right? So this is the kind of theory that's SU2 gauge theory coupled to NF fermions in the fundamental representation, spin half representation. It's kind of Lagrangian that's there in every field theory textbook, right? I learned field theory from Zigzon and Zubair. I don't know if humankind learns it from you probably learned it from Zigzon and Zubair. But this is a giveaway on how old we are. Maybe Peskin and Schroeder, is that what people learn it from? Yeah. But in any case, this sort of Lagrangian is there in every textbook in quantum field theory, right? Now sorry? Yeah. So right now everything is a dynamical field. Exactly, yeah. So you look at this theory. Now what textbooks don't tell you is that this is really a theory of bosons. Okay? So even though the Lagrangian is written in terms of fermionic fields and there are SU2 gauge fields, right? There's a real sense in which this theory is a theory of bosons. So what do I mean by that? Right? It's a point of view that's, I think, obvious to condensed matter physicists, but to some high energy physics it's also obvious, but not always. That's what I've discovered. The point is that, these fields are entirely Lagrangian, they're not gauge invariant, right? So they don't create local objects, right? It doesn't matter what they're doing in the infrared. They may be free, they may be confined, it doesn't matter. These fields in no phase of the system can correspond to things that can be created locally. Okay? What you can create locally are baryons and mesons and glue balls and so on, which are all bosonic. Right? So all local operators in this theory are bosons. Right? Which means that the right point of view on this field theory is that it describes some bosonic system, right, in the UV, from which at some intermediate scale there's a description that emerges in terms of these fermions and the gauge fields. Yeah, I would have said the same thing, except for one small difference, very important difference. Then the theory becomes standard QED in 3+1 dimensions. It's almost a theory of bosons, except that, standard QED, it certainly doesn't have fermions in it, okay? Except that standard QED, when I write Lagrangian that way, also has loop-like degrees of freedom. Loop, because in a Lagrangian like this, in QED, the magnetic field lines don't end. There's no magnetic monopoles, right? So the Hilbert space in which this theory lives has point particle-like objects which are bosons, which are gauge invariant, electrically neutral, gauge neutral particles, electron, positron, bound states, right? And magnetic loops. So it's not a theory just of point particles, it's a theory of particles and loops.
But how about electrons themselves?
Electrons themselves are not gauge invariant.
Yeah, but they are physical particles.
They are emergent quasi-particles of some underlying system. A single electron cannot be created locally.
That's a Wilson line.
No, that's, physically speaking, you create a single electron, you have to create electric field lines that go to infinity. No, no. So you create a single electron, right, in isolation. Forget Wilson, right? Let's go to Gauss, right? There's a Gauss law that tells you that electric fields have to radiate outwards, and I can detect this electron by doing a measurement at spatial infinity, right? So if I try to create a single electron without the associated electric field lines, that's the bare electron creation operator. That's not gauge invariant. The gauge invariant thing creates both the electric charge and the electric field lines.
I agree with this, but I'm just saying that you can certainly scatter electrons and study the scattering.
You can do all that, but you cannot create a single electron locally.
But here you probably mean more, right? Here you mean you cannot see quarks.
No. Soon I'm going to talk about phase of this theory in which you do see quarks at low energy. Exactly.
Just statement about gauge invariant, just statement about local operators.
It's a statement about local operators. So the point of view from which I'm going to view this entire theory is that this is really a theory of these underlying bosons, which means of the baryons and mesons. The quarks are emergent degrees of freedom from the baryons and mesons. Okay? So it's actually completely opposite to the high energy point of view, in which you say that baryons and mesons emerge from quarks. Here we're going to regard that in the UV, I have some lattice model, which is written in terms of the baryons and mesons, and then in some phase of that model, at intermediate scales, there's a description in terms of quarks and gluons. And then in the IR, these degrees of freedom may surface as relevant degrees of freedom, or they may be confined. That's a secondary matter, right? And so that's the point of view. And there's a fundamental feature of this theory that it can be viewed that way, right? That it's a theory of bosons. Now, as I said, this is a point of view that's familiar in condensed matter physics and to some high energy theorists. So again, your sophisticated friends from Princeton understand this in a different way.
But when you say that there is some underlying microscopic lattice type description for which this is a
Yeah.
description, which again you can think of, but that microscopic description is bosonic.
Yes.
But I mean, if something is already UV complete, it does not necessarily need this kind.
It doesn't need it, but the point is it can be given such an embedding. Right? I'm not actually going to do that, but it's important for me to know that it can be given, so this theory is UV complete. But despite that, it's a true fact that there's no gauge invariant fermionic operator in the theory. So the fancy way of thinking about the same thing is to say that you can put this theory on a non-spin manifold by choosing bundles in SU2 gauge cross that, the tangent bundle mod something, right? Being able to put the theory in a non-spin manifold is what we mean when we say the theory is a theory of bosons. For bosons, you don't need to choose spin structure. You don't need to define spin. Right? So it took me a while to understand that this is what non-spin manifold was important for. But, condensed matter physicists usually just say it's a theory of bosons. I mean, now, Yeah, so I haven't yet come to this sentence, but that's exactly what I was going to talk about. So it's because the SU2 has pseudo-real representations. Does that make sense to you? Okay, I was not sure if I had to give a one-line answer, that's what I would have given. But you can work it out, right? So the first question to ask about any field theory is to identify what the local operators are. So we're not trying to solve for the dynamics, right? We just want to know what is this a theory of. And the second question is, what are the global symmetries of the theory? So these are all answerable questions that don't have to do with the dynamics of the theory. Those are the really hard questions, right? Even before answering those really hard questions, there are, these are answerable, but the answers may be subtle, right? So we have to understand what the theory is a theory of and what the global symmetries are. And in this case, the global symmetry is SPNF mod Z2 times time reversal. Okay? So we're going to view this gauge theory as the IR description of some UV system of interacting gauge invariant bosons with this global symmetry. Okay? So that's the point of view. Okay. So there's a lot that's known about the IR properties of these kinds of field theories from your favorite field theory textbook. Okay? So the answer depends on what the value of NF is. So field theory books usually ask about small values of NF. They want to know when the theory is asymptotically free. That happens below a certain NF, right? This value of NF. Below this value of NF, the theory is asymptotically free. If it's small enough, it's believed to be confining. That's what field theorists are interested in. Field theory books are interested in, usually. Now, if NF is big, then the theory is IR free, and these quarks and gluons become free in the deep infrared. And at intermediate values of NF, there's an interesting possibility that it flows to a conformal fixed point. That's the Banks-Zarks fixed point. Okay? So this number is known exactly from the perturbative beta function. This number requires serious numerics, and it's controversial. Numerics going back last 2 or 3 decades. People still keep writing papers on this. So these theories are interesting, but I want to keep things as simple as possible, so I want to restrict myself to IR-free theories in this talk. Right? So this is the regime that's ignored in field theory textbooks on the grounds that that's boring, forget about it. It's IR-free, what's there, right? But I want to talk about this and show that it's actually extraordinarily interesting, okay? So the question we want to ask is, what kind of criticality do these theories describe? Because after all, we see that, this entire field theory is a description of some boson system, right? And here, by tuning some parameter, I end up in a regime where in IR, there's massless fermions in this boson system. So what is the place of this massless theory in the general context of the phase diagram of this boson system? Right? So that's the question I want to ask. Okay, so it turns out once you ask the question, the answer is very simple. Right? I guess we've known about this since grad school days, right? But it never occurred to me, at least, to ask this question for all these decades. Right? So let's first think about the RG flow structure for large enough NF. So there's a Yang-Mills coupling constant G, and there's the fermion mass M, right? At the massless point, the Yang-Mills coupling constant flows to 0 because NF is large. So the theory is IR free. But when I turn on the mass, the mass is a relevant perturbation at this free fermion fixed point, right? And when I turn on the mass, the Yang-Mills theory, the Yang-Mills coupling constant will initially flow to small values, but at some scale it realizes that the theory is massive, and then below that scale you just get a free SU2, pure SU2 gauge theory with no matter fields, which is of course strongly coupled. So the flow turns around and it flows back to strong coupling, okay, on both sides, right? Which means that both sides are strongly coupled, presumably confined phase of matter. But the critical point has, is deconfined, right? It's massless. So this weakly coupled, in fact, zero strength coupling fixed point, zero coupling strength fixed point emerges as a critical point that separates two strongly coupled phases. Okay? Oh, come on. Something's going on with this. Oops. Now I lost it again. Yeah. So the question is, what's the difference between these two massive phases? Okay? Now, if m less than 0, first let's think about in the absence of the gauge field. By my choice, m less than 0 is always a trivial symmetric gap phase. And then I turn on the gauge field, I get pure SU2 gauge theory, which is confined, and it doesn't break any symmetries, right? That's the belief that pure SU2 gauge theory, when it confines, it just goes into a totally boring phase of matter. Okay? Now, for m bigger than 0, it could happen that the dynamics of the pure SU2 gauge field theory that I get has a theta term. Okay? But you can calculate the theta term, and it turns out that the theta term is nf times pi. And if nf is odd, then you get an SU2 gauge theory at theta equals pi, which is an interesting theory, and people still don't know what the theory does. There are interesting papers in the last few years on that theory. It turns out there's all kinds of anomalies in that theory, blah, blah, blah. So it's not really known. There's a guess that the theory spontaneously breaks time reversal, which is an interesting guess. It's probably right. It's definitely right if SU2 is replaced by SUN or SPN and n is taken to be large. But for SU2, it's not known. Now, to keep things simple, let's focus on NF even. Okay? So then there is no theta term. Theta is a multiple of 2 pi, and you can ignore it. So then you get standard SU2 gauge theory, which means that for m bigger than 0 as well, you get a trivial symmetric gap phase. So both sides are trivial phase of matter. There's no topological order, there's no broken symmetry, nothing, so long as NF is even. But it could be different as an SPT phase, right? So that's the only possible distinction. So what you end up with is a massless deconfined point, critical point, separating two confined phases. But here the IR theory is in complete control, right? It's just free. So that's why I don't need numerics in this case. So this is a good example of a deconfined quantum critical point. Now I should probably skip the next slide. So it turns out that to evaluate this situation of whether or not it's a different SPT phase, the methods one uses are exactly the kind of thing I talked about before. Calculate the ratio of the partition function of this theory for the two signs of fermion mass. Both numerator and denominator involve a strongly coupled SU2 gauge theory. When the mass is non-zero, right? So you can't calculate either partition function, but the ratio turns out is very simple to calculate because all the non-trivial dynamics cancels out. And in the ratio, what we're interested in is the ratio of these two partition functions of how it depends on a background gauge field that couples to the continuous global symmetry. And that, whether or not there's a theta term in that background gauge field. And it turns out indeed there is, and it depends on the value of NF mod some integer. Okay, so if you calculate this ratio of partition functions, then it turns out that you get a theta term for the background global symmetry, and the precise value of the theta term depends on the value of NF over 2 mod 4. So you get distinct SPT phases, and then that's it. So then we have our interpretation. So now we understand this, the place of this massless IR fixed point in the phase diagram of the boson model completely.
Sorry, I didn't understand this. You had discussion of theta term in the
Yes, these are different theta terms. One was for the dynamical gauge field, and that I, at least initially in this part of the talk, I want to avoid having to deal with it. So I want to interpret the simplest possible theory. So I stick to even and f.
And the fact that the theta term is pi for different criteria has to do with how the SU embeds inside the global.
Yeah, that's right. Yeah.
There is probably a factor of half there or something like that.
Yeah, it certainly is related to how SU2 embeds in that theory, in the ungauged original theory. Right? So in any case, so at the end of the day, the story for this sign of the mass, the theory is in a trivial phase of the underlying bosons. For the other sign of the mass, the theory is in SPT phase of the underlying bosons, and there is a continuous phase transition between these two that is described by this IR-free gauge theory, which has emergent fermions, emergent gluons, which are free, nothing talks to anything else, and that's it. You can calculate anything you want as far as universal properties of phase transition are concerned in this theory. Okay? So that's it. So we understand this example of deconfined quantum criticality in 3+1D completely. Okay? Both phases only have trivial excitations, but the critical point has all these non-trivial excitations. Okay. So this may be a bit esoteric, but there's good reward at doing this esoteric generalization, right? So we can play the same game now with any theory that you want. Any gauge theory, any gauge group will have, if NF is big enough, will be IR free, and we can always ask how to interpret it. Now, a particular generalization is very interesting. It's to take SP and C gauge theories with NF fundamental fermions. Now, the amazing thing is that it turns out it also describes a UV bosonic system with the same global symmetry for all values of NC. Okay. Now, again, from a Kenneth matter point of view, you can think of this different partron descriptions of the same system, right, with different gauge groups. But if you, from the field theory point of view, if you take this program that I said, identify what the local operators are, identify what the physical global symmetries are, for all values of NC, it describes the same underlying boson system. Okay? So then by analyzing these IR-free fixed points of these theories for general NC, it turns out you get a large set of IR distinct field theories for the same set of trivial to SPT transitions of these bosons. The point is that the number of SPT phases that are allowed for any given global symmetry, the global symmetry depends on NF, right? It's SP and F mod Z2. So there's this finite number of distinct SPT phases that exist. Right? There's in terms of theta terms that you can write down, there's a finite number of theta terms for the global symmetry. But there's an infinite number of NC for me to play with. Right? So you're going to exhaust the number of distinct phases that you can describe with these theories very soon. Right? But the different massless fixed points for different values of NC, they're all sharply distinct from each other. Right? We can just count the number of massless fields, it's all different. Right? So for the same phase transition, you then get an infinite number of different universality classes. So that's it. Right? It's a very trivial construction of answer to this question of whether you have multiple universality classes for the same phase transition.
You basically start with the multiple universality classes and then say that the phases are.
Exactly, yeah. Here, everything is to start from the answer and then go back.
So you can understand that the critical point depends on what your gauge fields were, right?
Exactly, yeah. But the phases don't.
The phases also, why won't the phases? Because phases also include some gauge theory without any.
But the gauge theory is confined.
It's confined.
And once it's confined, the first thing I argue is that all local operators in the two theories are the same, right? And the global symmetry is the same. So the underlying UV system is the same. So the intermediate scale gauge theory description is different.
Sorry, in the phase you mean when it's
Yeah.
If you look at the gauge invariant operators, then they would.
No, the gauge invariant operator is a statement about the theory irrespective of which phase it is in. Now, in the confined phases, the only excitations you have are things that are created by these gauge invariant operators.
Yeah, but gauge invariant operators for SP and C gauge theories for different values of NC would be different.
No.
I think it would be.
In terms of which physical system it describes, it's the same physical system, right?
So what I mean is that because SP and C is some, I mean maybe this is not relevant, but just in terms of if I just were to count gauge invariant operators,
Yeah,
SP and C gauge theories for different values of NC,
yeah,
you know, SP and C is a particular matrix size, right?
right,
So there
right.
would be matrix relations which would come in effect for SP5 theories later than SP3, let's say something like that.
No, but the basic gauge invariant operator is this boson that transforms in the fundamental representation of SP and F mod Z2, right? And everything else is a composite of that, right? Those are the only excitations I am allowed to have in this theory, as those are the only local operators in these theories, and that's true for any value of NC.
Sorry, could you say what is the gauge invariant operator?
A boson that transforms in the fundamental representation of SP and C mod Z2.
You mean the meson field?
It's a baryon.
It's a baryon.
You'd also have you'd also have meson fields, but we can talk. Let's talk about baryons.
Okay.
Right?
So the baryon.
The baryons are both the baryons and mesons. They're exactly the same in both these theories.
Don't quite understand.
No, there may be non-universal features that are different, right?
But even with the counting, so if you look at the number of baryons and the number of mesons in the SP and C gauge theories as a function of NC,
Yeah.
I think this counting will change because of matrix relations. You know, gauge.
No, I'm not sure what you mean by the number of baryons, because you know.
In other words, there would be relations between baryonic and mesonic fields, which would then be different, which would detect, even though everything is projected onto singlets, it will still detect.
Oh, very good. So those differences I would regard as non-universal differences. They may emerge near, they will emerge near the critical point, right? But from the perspective of the underlying boson theory, that boson theory doesn't know any of this stuff, right? So it's just, you know, so this phase, for instance, is just a trivial gapped state of these bosons. So far from the phase boundary, right? There's only one boson and its composites. That's all there is in the theory. Now, as you approach this phase boundary, whether you approach it here or whether you approach it here, in the close vicinity of this phase boundary, there may be some other structure that reflects the fact that there's this emergent gauge theory that lives at the critical point. So again, the point of view is inverted. So we don't regard the gauge theory as the fundamental thing. We regard the UV boson system as the fundamental thing. And then where the gauge theory emerges, if there's differences, those are emergent differences, not fundamental differences. Things, I mean, once you take this point of view, right, there's nothing profound about what I'm saying. Okay. Having difficulty. Good. So let's continue along these same lines. In the particular case where we choose NF and NC to be equal to 0 mod 4 and NF is big enough, then we find that the two signs of mass, there is no difference in the theta terms for the background gauge field, right? Which means that, you know, both phases are trivial phases, right? Which means they are the same phase of the underlying boson system. So this is an example of this unnecessary quantum critical point where this massless gauge theory arises somewhere in the middle of a single phase. Okay, so this is what I first mentioned, right? Okay, these sound like it's an extremely esoteric example of this phenomenon, but this is how we first found it, right? By playing around with these theories. But later, we found several examples which do not involve emergent gauge fields where the same phenomenon happens, both in 3+1 dimensions and in 2+1 dimensions. Okay, so let me give you one example in 3+1 dimensions. It's still a bit esoteric, but hopefully, because these are the first examples we are finding, we go from the most esoteric to slightly less esoteric. Eventually, hopefully, people will find, much simpler ones. Okay, so the example is to take 16 copies of helium-3b. Helium-3 is going to become the superfluid at low temperature, and most of its phase diagram, when it's a superfluid, is occupied by this B phase, which is a fully gapped state. And in this B phase, the Bogoliubov quasiparticles have certain Bogoliubov bands. They have a dispersion, which is now understood to be a topological band structure. Okay? And at the boundary of at a surface, this topological band structure is such that there's a single massless Majorana cone at the boundary. This is an example of what's known as a class D3 superconductor in 3+1 dimensions. Okay? Now I want to take 16 copies of this class D3 superconductor. It turns out there's a special reason to take 16. Now for n Majorana fermions, if we take one sign of mass to be trivial and then the opposite sign of mass, it's non-trivial and it's topologically protected by SON cross time reversal. And in the free fermion theory, there's a direct phase transition so long as I have SON symmetry. Okay? Now, if or I have time reversal symmetry. Now, the reason to choose 16 is that with 16, it turns out time reversal alone does not distinguish these two phases. So this is something we've learned in the last few years. There's for the boundary 2+1 dimensional theory with n massless Majorana fermions. In free fermions, there's a Z classification of these theories in class D3. But once you include interactions, that Z classification collapses to Z16, and the boundary time reversal anomaly has there's 16 different time reversal anomalies that you can have. This was, Kitaev knew this result, but as usual, nobody knew how he knew it. There's some talk that he gave which I don't understand, and later several of us worked on this and understood, how this actually works out. Now, so there's no time reversal distinction between these two phases in the bulk 3+1 dimensions. But still, to protect this direct transition, you need the mass of all these 16 fermions to change sign at the same time, which might require, SO16 symmetry. Yes. If it does require SO16 symmetry, then there's a difference between these two phases that's protected by SO16. There's a theta term for the background SO16 gauge field. Now, it turns out that it's enough to keep just SO2 cross SO7 symmetry. That forces all the masses to be the same, but then it removes any symmetry distinction between these phases. Right? So, okay, it doesn't have emergent gauge field, so it's not as esoteric as having SP and C gauge theories coupled to NF matter fields with everything being mode 4. There's no, this is just, it's something you can describe within the band theory, right? You have, it's a band inversion transition with 16 Majorana fermions undergoing band inversion at the same time in the presence of some global symmetry. But it's the same phase on both sides, and but there's a phase transition nevertheless. Okay? And we have a similar example in 2+1 dimensions as well, but
This is probably a trivial question, but I just want to understand the characteristic of this particular phenomenon. So if you
No, here, this is a fermion theory. Right? Here, there's no boson.
Scalars, and I'll give them a mass term.
Hmm.
Now, for positive mass and negative mass, you just get the same phase. Nothing is different. But
Ah.
would one then say that there is a phase transition that goes through the same phases at n equals 0?
No, for negative mass, you break a symmetry, right?
Not mass square, not negative mass square, just negative mass. It doesn't do anything.
Oh, but then the theory is sick, right? Isn't, oh, negative mass.
Yeah, mass square equals nothing.
Oh, but no, but then it's the same phase, right? It's the same theory.
Same phase. But so what I'm saying is this is what it means, right? That there is no fundamental distinction between a mass and a negative mass.
Yes.
For Dirac fermions, there could have been a difference.
If you tune the other content of the theory such that the theta terms cancel and
Yeah,
effectively you're making there to be no difference between the
exactly.
mass and the mass. So it's
No, but your example is different, right? Because for a scalar theory, since the mass only enters Lagrangian as mass squared,
but in some secret form that's what probably is happening here, right? In what sense there is a line
You're saying
which
model
I
C is the same thing as saying I'll change the sign of m, but I'll write m square.
yeah, yeah. I mean, it's a formulas that govern these things. Things will enter in m square. I'm just saying, in what sense can you move around and see that there is a phase?
so I bet that I can produce a model, right? Fermions with some interactions. I need interactions to enable this transition, right? Where as I change one parameter within this phase, I end up at this critical point, right? Now, in the example that you gave, right, the right interpretation of the m equals 0 point is not that it's separating m positive and m negative phases. The right interpretation is that it's separating m squared positive and m squared negative phases. Right? The free Gaussian theory sits at in 3+1 dimensions at, you know, it separates an Ising transition, it's an Ising critical point, right? But here it's not like that. And in the previous example with the emergent gauge field, it's even more dramatic. I have a boson system which is gapped everywhere, but then I tune one parameter, I end up with the emergent free fermions. Right? But I can avoid hitting that point. Right? Okay. There's some angle or something. Let me briefly mention this. I don't know, when should I stop? I'm just talking.
You have done 3 out of your 5 multiples, right?
Yes. 2 left. Let me briefly mention this. But, you know, it's all very informal, right? So I can stop whenever.
We get food like anti-summons.
All right. Lunch is the cutoff.
There's
Yeah.
instant food in 15 minutes.
All right. Okay. You know, just to emphasize, you know, what I said was this point of view that's obvious to charismatic physicists, but is interesting from a high energy point of view. Let's now talk about, you know, go back to SU2 gauge series with NF flavors, but now have adjoint fermions, right? So it's the fermions that transform in the spin 1 representation of SU2. So the Lagrangian again is this, but with psi transforming the adjoint representation. Now, unlike in the previous case where the fermions were in the fundamental representation, here there is a theory of fermions. Okay? Because the gauge invariant operators in this theory, there are things like this that you can form using the epsilon symbol, and that's a gauge invariant fermion operator, right? So therefore, this is the theory that describes fermions. The UV system, you know, the baryons in this theory are fermions. Okay? Now, I want to be able to think about this theory as something that emerges from a lattice model of interacting fermions. Okay? For that point of view to be legitimate, it turns out that this theory is not enough. I had to supplement this theory by having some extra scalar fields in the fundamental representation. I can take their mass to be very heavy, but they have to be there as part of the theory. I'm going to explain that in a minute. right? So that's this thing in brackets, right? So I'm going to add heavy spectator matter fields Z in the fundamental representation. Okay. Now the global symmetry of the theory with C in the this gauge invariant fermion of the vector representation is a SO2 and F cross time reversal. I'm not going to explain this, but it's easy to work out, right? So I'm just following the program that I outlined of first understanding what the local operators are in this theory, and next asking what the global symmetry is. So the point of view that I'm going to take on this theory with this important spectators added is that it's an IR description of some UV system of fermions with this particular global symmetry. Okay, SO2 and F cross time reversal. Okay, so now for the low energy dynamics, these spectators don't matter for the most part. They are heavy fields, while the light fields are these adjoint fermions, right? Now, from the dynamics of these theories are reasonably well understood for m equals 0. Again, if NF is big enough, the theory loses asymptotic freedom, it becomes infrared free. Now the conformal window, the way you lose asymptotic freedom occurs at a smaller value of NF with adjoint fermions than for fundamental fermions, and that's good from our point of view, right? Because large NF means the theory becomes some esoteric theory. It's SP and we have bosons or fermions with this weird. For small NF, it's the kinds of theories we actually care about, right? So asymptotic freedom is lost already at NF bigger than or equal to 3. Now, what's the role of the spectator fundamental scalars, right? So the theory has, without these scalars, the theory has unbreakable electric loops in the fundamental representation, right, which don't break. So the theory has loop-like excitation. So I can't put it on a lattice, right? So I can't interpret the theory as emerging from a lattice system if it has loop-like, I can't put it on a lattice with the tensor product Hilbert space structure, right? Which is what, the kinds of systems we think about in condensed matter all have tensor product Hilbert space structure, right? So I want to allow myself to break these loops. So once I have a matter field in the spin half representation, that will act as a source or sink of these loops, then the loops get cut.
Sorry, what is the
Oh, electric field lines in the spin half representation. Okay. Now there's a fancy phrase, very useful actually, phrase that was invented for this, that captures this kind of situation. So theories that have these unbreakable loops are said to have a one-form global symmetry. Okay, so the loops can't break, right? In this case, these are unoriented loops, so there's a Z2 one-form global symmetry. Now, you were asking about QED in 3 plus 1D, just the standard Lagrangian. So I said there's unbreakable magnetic field loops, so you can say that that theory has a U1 one-form global symmetry. That's something these people also explained in their paper. So standard Maxwell theory has two U1 one-form symmetries, one for electric field lines, another for magnetic field lines. Right? So standard Maxwell theory is not a theory of point particles. QED is standard QED is also not a theory of point particles. That's a theory of point particles and loops. Likewise, this theory without these spectators is not a theory of point particles. But once I have these spectators, it's an ordinary theory, right? But at low energies, so long as these spectators are heavy, there's an emergent one-form global symmetry, which is important to keep track of. Okay. Oops. No, that's it. How do I, maybe. Okay, so So the large NF story is actually very similar to all the previous examples. I'm not going to, there's some interesting subtleties which again, it turns out that precisely which SPT you get on this side depends on exactly how time reversal is implemented on the spectator bosons. Without that, without specifying that, you have an incomplete specification of the low energy theory. So just saying that you have a joint SU2 gauge theory without saying anything about the spectators, it's not a complete. The theory can be given different UV completions resulting in different physics. Anyway, that's a subtlety. And I guess this one of the things, it gives us many examples of band theory, forbidden criticality between band insulators, but let me not talk about that. It's interesting to analyze, but it's the same story as before, right? Instead, let's go to the case which is most interesting for us, which is NF equals 1. So this is an asymptotically free theory. So it flows, the gauge theory, it's a strongly coupled gauge theory. Okay? Now this theory turns out is extraordinarily important in both condensed matter and in high energy physics. Okay? In condensed matter, at NF equals 1, that we already decided that this is a theory of physical fermions with a symmetry, SO2NF cross time reversal. At NF equals 1, that's the same as U1 cross time reversal. So this is the theory I started my talk with, right? It's the standard theory of a topological insulator, right? Because it's cross time reversal, it's in so-called class A3 instead of class A2, which is spin orbit coupled topological insulators. But it's a system that's been studied a lot in the condensed matter context. It plays a big role in this theory of the half-fill Landau level and so on. And I mean, it's an important system. There's hundreds of papers written by card-carrying condensed matter theorists, people who care about experiments and so on this system. Okay? So there's a lot of reason to care about this theory from a condensed matter point of view. Now it's also important in high energy physics because this gauge theory is a deformation of the famous N equals 2 Seiberg-Witten theory. Okay, Seiberg-Witten theory is more fields, you gap some of them out, you get this SU2 gauge theory with the joint fermions. So there's a number of recent papers on this theory, some from high energy physicists and from us who don't know any high energy physics, right, with two completely different motivations. In particular, I guess you're probably friends with these people, right? You were co-postdocs, at least with one of them. Okay. So there's a lot of good reasons to study this theory, both from a point of view of completely ordinary condensed matter physics and from the point of view of completely respectable quantum field theory, right? So what's going on with this theory? So m equals 0 turns out it's possibly conformal. There's one numerical paper from a few years back which seems to find some power law correlations in the massless theory, right? So it's not just trivially confined apparently, so worth studying. But the numerics has not settled down and people are still studying it, we'll see. Now for m not equal to 0 but large, we expect confining symmetry preserving phases, and it's easy to check there's no induced theta term for the dynamical SU2 gauge field, so there's no surprise. You just get confined phases of fermions with a single global U1 and time reversal. Okay? Now, yeah?
Fundamental example also you could have tuned the value of NF down to the conformal window and then you would have had more interesting physics.
Exactly. I could have done that, but at least close to the outer edge of the conformal window, everything else should go through and be the same. Right? I just chose the more.
Even if you go to the middle of the conformal window, let's say,
Yeah.
then the characterizations of the phases would be kind of same.
Right. So but there is a subtlety which will become clear in this example. Right? So the point is that if the conformal field theory that emerges is strongly coupled, then we don't know what happens when we make a small massive deformation of the theory. What we know with confidence is what happens at large mod m. Now here, if m is not equal to 0 and is large, we know that we get trivial insulators, but they may differ from each other as topological insulators. Okay, that needs to be calculated. It's an easy calculation which I'll show in the next slide. So there's a possible topological distinction between these two extremes, but we don't know how to complete as of now the rest of the, as of this instant of time in the talk, the rest of the phase diagram. If on the other hand this theory is weakly coupled or a free theory, then we know that for infinitesimal mass we know what happens. The theory is strongly coupled, then we don't know that. Right? So the safe thing is to just say what happens at large mass. Okay. I should point somewhere or something. You know what? I'm just going to walk over and change. Yeah. So with this symmetry class, we know the possible answers because we know the distinct SPT phases. So we ourselves, classified them a few years back, and whatever our answer was confirmed by these two mathematicians, Dan Freed and Michael Hopkins, using totally different methods. They get the same answer as us, and the answer is that SPT phases with these symmetries are classified in free forming. There's a Z classification. But then with interactions, they are classified by Z8 cross Z2, which means they are labeled by two integers, k running from 0 to 7 and s running from 0 to 1. Now in the gauge theory, by calculating these partition function ratios, it's easy to determine that the phase with m bigger than 0 is one of the phases k, 0. Right? This index s, this Z2, it's a trivial element to the Z2. And it's some integer here with k odd. Right? Now, the precise time reversal implementation on the heavy Z bosons determines which odd k, but there's a choice. If I choose Z to be a Cramer's doublet, then I get k equals -1, which is good because that's the most elementary topological insulator. Okay? So then let's make the choice. And then for m less than 0, I have a trivial insulator. For m bigger than 0, I have the most elementary topological insulator. Right? And somewhere along the way, there is this emergent gauge theory. So this is the importance of this model, of this field theory for condensed matter physics. Right? It gives me a possible way for an intermediate state between a trivial insulator and a topological insulator. Right? And it's not an esoteric topological insulator, it's a standard topological insulator. Okay? So that's the reason why, from a condensed matter point of view, it's good to understand this theory. It tells us of a possible evolution between two phases of matter that we certainly care a lot about. But we know exactly we already know one way in which the two theories can evolve, the two phases can evolve between each other, and that's the first example in the talk. Right? It can go through, within free fermion theory, it can go through the standard band inversion transition, which means it goes through a massless free Dirac fermion. Okay? So free fermion theory gives you one possible evolution between the two phases, and the gauge theory gives you another possible evolution between the two phases. Right? Oops, keep doing strange things. So, a wild guess.
So can you understand why one evolution is by gauge theory and the other by free fermion?
Oh, the two phases I said. One phase is the trivial phase, the other phase is the elementary topological insulator. So I can, free fermion theory gives me a possible phase transition. But the gauge theory also has the same two phases, and it's taking some route to go in between. Right? So that's what's depicted in this picture. So a natural question to ask is the gauge theory secretly giving you the same description as free fermions, right? In which case there's some weird duality, right? So this is the free fermion story. So this is the gauge theory story, and this is the free fermion story. So could the gauge theory have the same phase diagram as the free fermions? Now it turns out that the two theories have the same local operators, and they have almost the same ordinary global symmetries. So maybe there's some chance, right? So the wild possibility is to contemplate the situation that this theory is in infrared the same as this theory, right? That would be really wild, because it's a strongly coupled gauge theory, right? If you can say something about its aerodynamics and it's something simple, then that's a big deal, right? It turns out that's not quite, this wild possibility doesn't quite work, but some refinement of it may work. So how should we tell whether these two theories are really IR dual to each other or not, right? Of course we can't tell, right? One is strongly coupled, so what are we going to say? There's no methods to tame the strongly coupled theory. But we can do some consistency checks, and if the theory, if the theory fails these checks, then we know that it cannot be dual to this free theory. If it passes these checks, we know that it may be dual, but we can't prove it. So the minimal check is that we had to check that all the emergent symmetries and their anomalies match at the massless point, right? If at least that much didn't work out, then we are in trouble. If this works out, we may still be in trouble, but not for obvious reasons, okay? And since the emergent symmetries include both ordinary symmetries and these one-form global symmetries, we had to check all of them and see whether everything matches. So let's understand the emergent symmetries, right? So the free massless Dirac fermion, everybody knows all the emergent symmetries of this system. There is a single Dirac fermion, you can write it as two wild fermions. There is an emergent symmetry which is SU2 rotation of the two wild fermions. Part of that SU2 is the global charge conservation of the Dirac fermion, and on top of that there's an axial U1 symmetry, relative number of two wild fermions that corresponds to this extra U1, and this is modded by Z2. And there are several anomalies for this emergent symmetry. There's the chiral anomaly for U1. There's also something that field theorists know very well, known as the Witten anomaly for this SU2. So there's things of that sort, right? There's a bunch of anomalies that the free massless Dirac fermion theory has. The question is what happens in the gauge theory side.
What is the proposed dual operator of fermion?
Oh, it's just what I wrote earlier. It's just the baryon. Yeah. Now, on the gauge theory side, it's easy again to analyze the global symmetry of the theory, because that doesn't require knowing anything about the dynamics, right? You can analyze it at the UV fixed point. And there's one subtlety. It turns out that the axial symmetry of the theory is reduced to Z8 by quantum effects. There are instantons in the SU2 gauge field, due to which the axial U1 conservation is reduced to a Z8. But okay. So the emergent zero form symmetry is SU2 cross Z8 mod Z2 in the gauge theory side. And then there's the emergent one form symmetry because of the unbreakable electric loops. So if you compare the free massless Dirac fermion, at the level of the zero form symmetry, the Z8 is replaced by U1 in the free Dirac theory, and there's no one form symmetry in the free Dirac theory, though it's there in the gauge theory, right? Now, so here's the non-trivial statement. Suppose I conjecture that the Z8 is dynamically enlarged to U1 in the infrared, which may happen, right? And in particular, I can start in the free Dirac theory and add, fermion interactions to break the axial U1 to Z8, and those interactions are all irrelevant. So I know that the U1 can emerge in the infrared, right? So let me conjecture that Z8 is enlarged to U1, okay? That this Z8, as the theory flows to strong coupling, gets enlarged to U1. Now, if it does that, then something amazing happens. It turns out that all the anomalies of this symmetry can be exactly matched with the anomalies of the free fermion theory. Now, that didn't need to have happened, right? But it does happen, and there's several anomalies and all of them match. Okay, it's magical how it all matches. So it gives us a lot of hope that maybe this wild possibility is not that crazy. Okay. But then we have to think about this one form symmetry. So the good news is that if the Z8 is dynamically enlarged to U1 in the IR, then the free Dirac fermion is capable of matching all the anomalies of the zero form symmetry. Okay? But then there's bad news, right? And the bad news, the bad news is that the one form symmetry is not benign, but rather there are extra anomalies involving the one form symmetry and the Z8 and gravity. Okay? If there's been no anomaly involving the one form symmetry, then one could have said, look, I break that one form symmetry with my spectators and then nothing, everything works, right? But here I can't do that because the one form symmetry is entangled with the ordinary symmetries and there's mixed anomalies between the two. And this is discussed in this very nice paper by Cordova and Dumitrescu. And so in light of their discussion, we have to modify the story. Right? It can't be that the wild possibility that I mentioned is just naively realized. But our conjecture is that there is a modification of this naive possibility which works. Okay? And the modification, is, so the first conclusion is that this SU2 Yang-Mills plus NF equals 1 Dirac fermion, adjoint Dirac fermion, cannot just flow to a free massless Dirac fermion. You can't match the anomalies of the one form global symmetry that way. But, the extra one form global symmetry is a discrete one form global symmetry. It's a Z2 one form symmetry. And it has mixed anomalies with the Z8 symmetry and with gravity. And it's a discrete unitary symmetry which is anomalous. And by experience with zero form discrete unitary symmetries, for zero form discrete unitary symmetries, we know that any such anomaly in 2 plus 1 and higher dimensions can be matched by a topological quantum field theory. Okay? So in the current spider context, we call it the surface topological order of a 3D SPT phase. So the claim then is that we can match these one form anomalies by augmenting the free Dirac fermion with a gap topological sector that has the right anomalies. Okay? So this is then the refined version of the conjecture that it flows to a free Dirac theory plus a gap TQFT. And the guess we made in our papers for a specific TQFT, it is just an ordinary Z2 gauge theory in 3 plus 1 dimensions that is symmetry enriched by having both Z8 and one form global symmetries act in a particular way. And the particular way is such that the physical loops that represent the one form symmetry are fractionalized in this Z2 topological order. So 3-dimensional Z2 gauge theories have loop-like excitations, right? Now those loops can be detected non-locally by taking the Z2 gauge charge around them. So those loops may carry fractional quantum number. So what does it mean for loop to carry fractional quantum number, right? So the point is that two such loops, when they come together, when they fuse, you get a loop that usually is topologically, is completely trivial. Right? You can take two such loops and they can destroy each other. You can't detect them non-locally and that's it. But now what I'm going to do is to assign two such loops the property that they cannot be broken, which means that I've enriched the theory with a global one form symmetry. And that the loops of the Z2 gauge theory are fractionalized loops right? I'm breaking a physical loop into two loops. And if I do that in a gauge theory, in a Z2 gauge theory where the gauge charge is a fermion, it turns out that's enough to match the one form, the anomaly between the Z2 one form symmetry and gravity. Okay. So this described in some complicated way in the field theory papers, Donaldson, written anomaly, blah, blah, blah. But it's a very, very simple gauge theory, just Z2 gauge theory with fermionic charges, for which we can write exactly soluble models. Right? Kitaev model in 3+1D will do it. Right? So that has exactly the right mixed anomaly with gravity. We also have a conjecture on how to enrich this with the Z8 symmetry in such a way that you match the mixed anomaly between the Z8 and the one form Z2 symmetry. We don't know if that's right, but physically it seems to make sense. Anyway, so that's what we propose, and it's not at all clear that it's right. It's not clear that it's wrong either. Okay, so far, there are other candidate phases that were discussed by Cordova and Dumitrescu for this theory. I think they favored a simple, chiral symmetry breaking phase. But numerics, we have to see from numerics what works and what doesn't. Anyway, maybe I should just stop. I've been talking for far too long. I should conclude. Anyway, so that's the essence of the story. Because I didn't talk about the Landau ordering beyond Landau, but it's really a simple twist on the first part of the talk. I was thinking about large NF theories with NF even. But now I do NF odd. Then there's a theta term for the SU2 gauge field at theta equals pi, which is still confined, but it probably breaks time reversal. And once time reversal is broken, there's no other SPT order because all the other theta terms can be tuned to 0 continuously. So then that's it. It's a transition between Ising ordered and Ising disordered phases with no other order. Could have been the Ising universality class, but can also be in a universality class where there's emergent fermions, blah, blah, blah. So that's it. Yeah.
I mean, the number of SPT phases that you want times T symmetric theory could have is just finitely.
Exactly, yeah.
You would again and again get those, right? So
multiple universality class. So all the things that I discussed for boson systems will also happen here.
So here also you could conjecture that the critical points for those for different values, essentially those would be theories with different values of NC.
Right.
Would be dual to each other.
Not dual. It's not the critical points. They represent different universality classes for the same phase transition.
No, but here I thought the motivation was that the two conform field theories separated the same phases.
Yeah.
So there also you would get similar phenomena.
Right. So the question here could have been, in light of what we found in the first part of the talk, it could have turned out that this gauge theory describes a different universality class for the phase transition in a trivial and topological insider compared to the free fermions, right? Now that would have, so if we had not been able to match the zero form, the emergent symmetries, not the microscopic symmetries are the same, right? But the emergent symmetries, if we had not been able to match, it would certainly have signified that. But the fact that the emergent symmetries match and the anomalies of zero form symmetries match, it looks like things really want to be the same.
Otherwise, it's an example of the other.
Exactly, that's right.